Hello friends, in the last lecture we have discussed few theorems. Then afterwards here uh, two examples to test the convergence of the series of infinite series of real numbers. Now in today's lecture we will discuss when the series is said to be positive term series and how to check its convergence. So if you consider an infinite series in which all terms after some particular term are positive. See, this statement is very important. An infinite series all in which all terms after some particular term are positive is a positive term series. So if you consider here first three terms are negative, but rest of the terms afterwards that term are all positive. So this series is a positive term series as all terms after the third term are positive. Or if here all terms in the given series are positive, all terms having positive sign in the given series, then in that case also it is said to be positive term series or series of positive terms. A series of positive terms either converges or diverges to plus infinity. For the sum of its first n terms, if here few terms are negative and few are positive, what you have to do? Omit the negative terms and omitting the negative terms tends to either a finite limit or a plus infinity. Means you don't consider here if few terms are negative and rest of all the terms are positive. Don't consider the negative terms. You consider the positive terms and you check whether your series has finite limit or its limit is infinity. If finite limit is there, we say it is a convergent, and if that series has infinite limit, then in that case we say the series is divergent. So see here the theorem which is related to it. A positive term series converges if and only if the sequence of its partial terms is bounded above. A positive term series converges if and only if sequence of its partial sums is bounded above. So see the proof of it. Uh, Let summation un be taken as a positive term series. So if it is a positive term series, we will get un to be greater than or equal to 0 for all n belongs to I. You will get un to be greater than or equal to 0 for all n belongs to I. So if we consider here Sn with the sequence of partial sums of summation un, if we consider Sn where n runs from 1 to infinity with the sequence of partial sums of summation un, then by using 1, you will get 0 to be un to be greater than or equal to 0, un to be greater than or equal to 0. Here sign is towards un, so un is greater than or equal to 0. We can write it as 0 is less than or equal to Sn. Sn is we know u1 plus u2 plus so on un minus 1 plus un for all n belongs to I. So from this statement, we can write here Sn is equal to sum of here these n minus 1 terms we can write Sn minus 1 plus we can write here un and then shift this Sn minus 1 on the left hand side, so it takes the form Sn minus 1 is equal to, you will get un, but un is what? That un is greater than or equal to 0 for all n belongs to I. So this implies what? Sn to be greater than or equal to Sn minus 1 for all n belongs to I. Sn to be greater than or equal to Sn minus 1 for all n belongs to I. Its meaning is what? Our sequence Sn is a non-decreasing, means increasing sequence, and we know that a non-decreasing means increasing sequence of real numbers is convergent if and only if that sequence is bounded above. So here you will get Sn is a convergent. Sn is convergent if and only if it is bounded above. Hence, by definition of convergence of series, we get summation un to be convergent if and only if this sequence of partial sums is bounded above, that is Sn is bounded above. So friends, in my sense, easily here we have proved here that one theorem, and you have also understand the proof of here that theorem. Now I will proceed towards next, that is your geometric series, and afterwards here P series. So as above theorem gives necessary and sufficient condition for the convergence of positive term series, means this theorem uh, gives the necessary and sufficient condition for convergence of the positive term series. So we conclude that if the sequence of partial sums Sn is not bounded above, then in that case series does not converge. If the sequence is bounded above, series is convergent, and if sequence is not bounded above, then in that case the series does not converge, or it does not converge. Now, what is geometric series? All of you know here this series. In statistics also, if you have studied here this series in FY BSc. So, what is series, geometric series? You see, we have studied geometric series or geometric sequence. We have studied in unit number 1 also. That is r raised to n, where n runs from 0 to infinity, and it converges to 0 if your r is strictly greater than 0 and less than 1. R is strictly greater than 0 and less than 1, and it diverges to infinity if that R takes value ought to be greater than 1. Next here, you must know how to determine the sum of terms in if the series in GP. So in general, geometric progression, that is GP, is AR square, AR raised to n minus 1, and so on. Means if the series are terms of the series are in this form, where A is called as what we call it as the first term of that series, and R is called as what we call it as a common ratio. Then in that case, we know how to determine here some of these n terms of that series. That is A plus AR square plus on AR raised to n minus 1. We can write it as a first term, that is A into 1 minus common ratio raised to n divided by 1 minus common ratio. That is 1 minus R raised to n divided by 1 minus R. But what is the condition on it? You will get some of this series to be this one, but what is the condition on R? R must be less than 1. If R is less than 1, we can write some of this series to be like this one. And if R is greater than 1, we can write its sum to be A into R raised to n minus 1 divided by R minus 1. Means only interchange here the positions in this bracket. You write second term as first term as second term. It gives some of your this n terms of the series, which is in GP, that is in geometric progression. So see, friends, the series summation n runs from 1 to infinity r raised to n minus 1, whose terms form a geometric sequence, is known as what we call it as a geometric series. Now we discuss its convergence. Now we will discuss when here this geometric series is convergent and when it is divergent. So obviously, the sequence is convergent if r is less than 1, and it diverges to infinity for r is greater than or equal to 1. So see what is that theorem. A positive term geometric series 1 plus r square plus so on, that is summation n runs from 1 to infinity r raised to n minus 1 converges. Why here taken r raised to n minus 1, or here because here first term is 1. So to get n terms, their power of r must be n minus 1. So this series converges if here r is less than 1. R is less than 1, and it diverges to plus infinity for r is greater than or equal to 1. And we will prove here that part. So suppose here 0 is less than or equal to r is less than 1. R is less than 1. Its meaning is R is less than 1. Its meaning is R is less than 1. So we'll define here Sn with the sequence of partial sums of here this series summation r raised to n minus 1, where n runs from 1 to infinity. That is Sn equal to 1 plus r square plus 1 plus r raised to n minus 1 for all n. So by using this first formula, because r is less than 1, you will get sum of n terms in GP. That is in geometric progression, we get Sn equal to first term is 1 into 1 minus common ratio is r raised to n divided by 1 minus r. and this can be written as 1 minus r raised to n divided by 1 minus r. So if you have taken this separate division, it takes the form 1 upon 1 minus r raised to n upon 1 minus r. And now you take here limit of this Sn as n tends to infinity. So if you have taken limit of Sn as n tends to infinity, no n is present in first term, so you will get that term as it is 1 upon 1 minus r, that is a constant, minus 1 upon 1 minus r from the second term is taken to be outside. And if we have taken limit of r raised to n as n tends to infinity, your r is lies between 0 and 1. That is, it takes value 0, but it takes value strictly less than 1. In that case, limit of here this term you will get it to be 0. And hence, you will get limit of Sn as n tends to infinity is equal to 1 upon 1 minus r. And this is a constant because r is a common ratio, it is constant. Its meaning is what? Our series summation and transform 1 to infinity r raised to n minus 1 sequence converges to 1 upon 1 minus r. So this series also converges to 1 upon 1 minus r when 0 is less than or equal to r is strictly less than 1. So easily we have proved here, means the geometric series is convergent if your r is less than 1. Now we will check when r equal to 1 and r is greater than 1, then what happens? These are the rest of the two cases. So when r equal to 1, from equation 1 we have, means from here this equation, from this equation, if you replace r equal to 1, there you will get 1 plus 1 plus 1, how many times? You will get it to be n times, means each sum you will get it to be n. And if we have considered here limit of Sn as n tends to infinity, you will get here limit of Sn as n tends to infinity to be plus infinity. Its meaning is our series, geometric series, diverges to infinity when r equal to 1. Now we will consider here r to be greater than 1. So when r is greater than 1, what happens you see? You will get Sn to be this one, but when r is greater than 1, you will get r raised to n to be greater than 1. Means we can write this Sn to be greater than 1 plus 1 plus 1 plus and so on. So what happens you see? There you will get Sn to be greater than, as r is greater than 1, taking power n on both sides, r raised to n you will get greater than 1 for all n. Means there you will get Sn to be greater than 1 plus 1 plus so on 1. How many times? N times. Means you will get Sn to be greater than n for all n. Its meaning is the sequence, but the sequence here, this n is there, where n runs from 1 to infinity is unbounded sequence of natural numbers. This is unbounded sequence of natural numbers. Hence, therefore, from equality inequality 2, means from this inequality, we get Sn n runs from 1 to infinity as an unbounded sequence. But by theorem 5, yesterday we have studied, the geometric series diverges. So thus, summation n runs from 1 to infinity, or summation n runs from 0 to infinity r raised to n converges if your r is strict, r takes values greater than or equal to 0 but strictly less than 1, and diverges if r takes values what? Greater than or equal to 1. So easily we have proved here that part also. Now we discuss the convergence of the series, what we call it as a summation 1 upon n raised to p. And this is also known as what we call it as a p series. This series, summation 1 upon n raised to p, is also known as what we call it as a p series, and which is used in comparison test to check the convergence of a series. So this theorem number 7 as well as here theorem number 6, both are here important because we need here these theorems uh, under here the comparison test or under the rest of the articles of here this topic to check the convergence of the infinite series of real numbers. So what is theorem number 7? A positive term series summation 1 upon n raised to p is convergent if and only if p is greater than 1. If p is greater than 1, then this series is convergent. when geometric series is convergent, if common ratio is less than 1, and when it is divergent, if it is greater than or equal to 1. And here, when the P series is convergent, if P is greater than 1, means this power of n in this denominator, if it is greater than 1, then in that case, the positive term series summation 1 upon n raised to P is convergent. So easily we will prove here that one theorem also. So uh, see here, friends, the proof of here that theorem, or maybe we will discuss here that proof in the next lecture. So today we'll stop here. Have a good day, friends.